Welcome back to the second session. So this session starts with a remote talk from Abu Dhabi. The speaker is Najwa Aaraj. Najwa graduated from Princeton University with a PhD in computer engineering. She has a lot of working and research experience from several companies and also from several research institutions. And she has extensive expertise in several fields of IT security. She has extensive expertise in several fields of IT security, such as applied cryptography, trusted platforms, and security architectures for embedded systems. Currently, Najwa is Chief Research Officer at the Technology and Innovation Institute in the United Arab Emirates, and TII is also one of our generous sponsors for this event. So now let's welcome Najwa and listen to a talk on IoT security challenges.
Hello, hi everyone. I must admit it's a bit weird. I don't see anybody in front of me, but thank you very much for accommodating the remote presentation, because we have a bit of restrictions on the travel nowadays. So I do appreciate the opportunity to still have the talk even remotely. So since the time was cut a bit, I had to reduce the slides, and I would be covering at high level what we are doing today in terms of research on IoT security at the Technology Innovation Institute in the United Arab Emirates in Abu Dhabi. So I will be talking today about the challenges of IoT security, and in particular covering what we are doing in terms of embedded encryption and machine learning technologies for IoT security. Just one disclaimer: the slides are not working properly when I'm projecting over Zoom, so I will be talking over some slides without doing any animation. My apologies for that. So today, basically, IoT is becoming an intricate part of our lives. So IoT devices are proliferating in our society, whether it's in our smart homes, in nuclear power plants, wearables for healthcare, for basically management of health in general. They're becoming an intricate part of supply chain logistics, etc. Other than IoT today, especially today, what we are working here in the Technology Innovation Institute is we're expanding this to cyber physical systems, to embedded devices in general, to UAV platforms that are using embedded processors, microprocessors, and then in general power constrained devices that we are dealing with. Sorry, I'm having issues with the projection, so I'm just gonna go to the slides. The estimate for the IoT market is that we will be seeing 25 billion devices up from 6 billion devices in 2025. The revenues would be $3 trillion. So we see that the impact and the proliferation and the expansion of IoT devices and their embedment in our daily life will be increasing over the time. The IoT revolution started basically a while ago. First, it was focused on the functionality. So we saw the year of placing the IoT as a platform, cloud management platforms. Then we saw a big movement later on in 2016 on the IoT developing applications and RTOS for the IoT. Then it started proliferating over time for the consumer goods. Then we saw standardization efforts. However, starting 2018, 2019, we saw that security is a very big concern for IoT platforms and IoT devices and CPS in general. In fact, it looks like it's a never-ending battle. And then the attacks, when we are talking about IoT devices, in addition to financial losses, they can have high implications from a security and safety perspective. So if we look at IoT attacks that happened over the past 20, 30 years, is that some of them, they put human lives at stakes, high financial damages incurred. For example, we're all aware and we all remember very well the 2016 attack that happened on the Mirai botnet attack, and in 2017, the WannaCry ransomware. And in fact, if we start looking, and this is something that we developed in our lab, if we start looking at the origin of IoT attacks or the exploits on of IoT platforms, is actually quite silly. You see a lot of vulnerabilities in the application level that is happening, and the embedded platform that is happening, and most of them are in the OWASP top 10. It's not something that we're not aware. So we see a lot of attacks that happened at the BIOS level. We see a lot of memory management issues or memory corruption issues when it comes to incurring buffer overflows that allow basically root level exploits of such devices, cache poisoning, crypto vulnerabilities, and others. So that brings us to the conclusion that basically IoT security is not something that is embedded in the device design and in the device manufacturing, and today it's coming as an afterthought. So the idea is, what are the areas that we can pursue today in order to start putting security as a top consideration for IoT deployment? What I will be talking about today quickly is, okay, we have IoT problems, IoT security problems. How can I use the concepts of security today, the concept of machine learning today, and tailor them in order to be adaptable to energy constraint, memory constraint, and basically computational constraint devices such as IoT and cyber physical systems in general? So today at our institute, and we already have few publications that went out, there are three arenas that we are pursuing. They're separate, but they end as an end-to-end security for IoT devices. We do them in a complementary manner. The first one has to do with crypto technologies. Basically, how can I integrate lightweight encryption algorithms and protocols within the IoT platforms? And that we do it both from a software perspective and hardware perspective. So we have an architecture based on a software hardware co-design deployment. And the second areas, they're orthogonal, that they have to do with machine learning. So the first approach to machine learning is, how can I basically derive how can I, through inference or through inference based on machine learning and neural networks, how can I limit the amount of data that has to go from the IoT device to the mobile device to the cloud in order to optimize energy, and then have edge-based security-based capabilities. So this is a very big area that we are pursuing today. And the third area, which is equally important, and frankly, it's not a problem that is only inherent to IoT devices, but it's also a problem that is inherent to cyber systems and vulnerability management in general, is that how can I have machine learning techniques, machine learning based techniques, in order to improve detection and incident response at multiple levels, at the edge level, at the mobile level, and also at the cloud, or what we call the central management interface. So what I'd like to do next is take some time in order to cover at a high level what we are doing in each of the domains, and maybe I can leave a few minutes at the end for questions if possible. To start with lightweight cryptography, so today one of the areas we look at in tandem with what the NIST competition that's happening is that, given the constraints or given the computational and power constraint on IoT devices, is that how can I have crypto algorithms that I can use for authentication, for data at rest security, and for data in transit security, that are fast in software, that have small hardware footprint when I implement them in hardware on ASICs or FPGAs, that enable low latency, and then at the same time still ensure that they have high security for me to be able to use them in critical critical systems. For example, one of the areas that we look at, it's more on the cyber physical systems, is that if I go into particular frequency bands that have particular requirements on latency, on bandwidth and throughput, how can I still have lightweight crypto protocols or primitives that enable me to do that? Obviously, most of you would be aware that um, so some actually would ask why would I go into the design of new algorithm or new lightweight primitives while I have already established algorithms for symmetric encryptions or basically for the public key infrastructure? And then the question is, why can't I have smaller key sizes that still enable me to have a decent level of security to do that? However, based on the experiment and on the literature, um, the footprint of existing symmetric encryption algorithms like AES might not always be the best available choice, especially when we're looking at small hardware footprints, and then when we want to have it in energy constrained devices such as RFID tags and other systems. So the protocols that we look at today, it was what has been proposed before, like present, which basically is based like AES on a SPN or substitution permutation network, and then focus on small hardware footprint, versus algorithms like Prince, which focus on low latency, versus algorithms like primitives like Skinny, basically, which focus on a, um, a, um, a balance between hardware and software implementation and have efficient method implementations for embedding countermeasures, especially when it comes to attacks on the hardware platform. We're following closely what's happening with the NIST competition when it comes to lightweight algorithms. And what we are trying to do is that to benchmark the best candidates that are being proposed and then integrate them in actual IoT devices, and in particular integrate them with the protocols and basically what we call the lightweight protocols, where we're trying to do the whole, if you want, the whole security paradigm and the protocol. So starting from the authentication, where we are developing asymmetric or public key lightweight candidates, then going into the data and transit security, and then developing the key exchange part and the symmetric encryption part, and then finally also looking at data integrity and non-repudiation and all of that with lightweight primitives integration at a protocol level on IoT devices. So we do this for the IP layer, and we also do this with RF-based systems where things like latency, frequency hopping, etc., also become a key consideration in the systems. And then this is basically the work that we are conducting today in terms of lightweight primitives, both on the software side, the hardware side, and the software hardware co-design side. So in addition to the crypto primitives deployment and integration, another area we are looking at today is how can I use machine learning in order to improve security on embedded systems, on IoT and cyber physical systems in general. So the first work that we are doing in collaboration with another university, with Princeton University, actually, is how can I improve inference on embedded devices in order to save on energy that is required on the edge device or on the basically the IoT device, the sensors, etc., using machine learning in order to save enough energy, or in order to save the energy that would allow me to run security solution encryption algorithms, whether it's lightweight, whether it's an adaptation of existing algorithm on the edge device. So what we do here is that we get a data set of the different communication or the different data processing that happens on the edge device, and then needs to be communicated back to the mobile or to the cloud platform. We understand the different use cases and the desired outputs from this communication and what needs to happen on the mobile and the cloud platform. Then we do connection pruning on the edge device, and this will allow us to derive neural network models that will allow for this inference to happen and the operations to happen on the edge versus the cloud infrastructure, thus enabling us to save energy, and then using this energy saving and to run security operations versus not having any security solution on the IoT device. The second work that we are doing, which is actually something that we are doing on generic platforms um, and on IoT devices. And this is the work where we are trying to merge the concepts of deep neural networks and causality and explainability of machine learning models. Is that given the whole spectrum of attacks and the whole spectrum of exploits that happened over the past years, what we are trying to understand is when an IoT device is under attack, what is the system level behavior. So what we try to do is that we try to capture the execution trace of the IoT device while it is being under attack and it is being under exploit. And then we're trying to model this execution trace as a mathematical model using regular expressions. And then we run such IoT device, which pretty much has a which should have a deterministic behavior, and then capture as many execution traces as possible, and then put them in what we call an anomaly graph. And that graph, basically what we do with it is that we capture all the attacks that we can that we are aware of, and then we use those attacks as the training set. We train a machine learning model, and then we derive the neural network model, and then this would enable us to derive new cyber exploits or anomaly behaviors. And what this will enable us in the longer run is that by having those new exploit chains on the IoT device, this will allow us to do two things. One, it will allow us to design the defense graph at the same time, in order to proliferate this knowledge that we have from the one IoT device to the second IoT device, in order to do the real-time patching of a network of IoT, of IoT devices. So this is a work that we have in progress. We have already achieved few results where we have trained the machine learning model with 39 known attacks, basically based on the table that I have shown you before. And then based on the training that we did, we found new exploit paths of 139 exploit path that could be possible, that basically when the human is considering those execution traces that consist of system calls, the data invariance that you have in the system calls or the program execution, that we are not aware while we have this we're not aware of while we have the system under attack or under exploits. So this work, we're trying to complement it with causality learning, and not only be depending on black box, if you will, the black box approach to machine learning model, and then we are also expanding on that. So I think I will stop here to see if there is any question from the audience. But I just tried to give the very quick talk. Unfortunately, I couldn't expand more on what are the different areas we are working on in terms of IoT security, both from a crypto perspective, the development of lightweight primitives, and also how we are trying to integrate machine learning models, neural networks for inference on the edge device, but at the same time also for capturing program behaviors and trying to find new exploit paths in IoT devices and cyber physical systems in general.
And now we have time for 1 to 2 questions from the audience. Yeah. Okay, so I have one question, my first question is, we all know that IoT security is very important also in the context of smart home environments, because many people use IoT devices and somehow connect them without considering the security. And are you aware of any real important incidents which come from lacking IoT security in smart home environments?
Sorry, 1 second. Let me just go back to this. So the attacks that actually resulted in if you want, damages that are related to safety more than financial risk, most of them were in more mission critical systems, not home-based deployment of IoT devices. However, today you have, for example, what you see in some small IoT devices that are being deployed either for lighting or for temperature management or for basically sensing humidity in houses. A lot of them, there are few incidents that were reported that they were vulnerable to DDoS attacks or privacy or data leakage, etc. So there are multiple incidents that have been reported on the media for small devices, but they're more related on data leakage. Some of them resulted in financial losses or basically in malfunction or mismanagement more than threatening devices. But definitely, I mean, most of these devices, 95% of those devices, they come with their inherent vulnerabilities, and then eventually the exploit can be done on such devices.
Okay, thank you. And there's one more question from Ileana.
Hi. So my question is the following. We know that cost for IoT devices is very, very important, and security solutions typically add to the cost. What would be the incentive to a manufacturer of IoT devices to add security to their product?
This is actually a very good question, and I will refer to this slide, which I didn't go into the detail of that. So as you said, basically some IoT devices, they come at a very cheap cost. So then there is no incentive in order to embed either, like, starting from the most basic thing, which has to do with code review on the IoT devices. This is typically not done. So what we are trying to do with our solution is not to rely on the manufacturer of the IoT device to have the security embedded in it, and we're trying to be complementary to that. So if you see in this deployment that I have in this slide, for example, the machine learning detection and incident response that we are proposing is not to run it on the device itself, but you can eventually add it as a router on a network level too. So while basically encryption and protocol has to be somehow embedded, especially when we're talking about data at rest, encryption has to be embedded on the device. Things related to inference and detection and incident response could be overlaid as network equipment on the IoT deployments too.
Okay, thank you very much. So now, I'd like to thank you again. Ahmad sent you 2 pictures, one picture from the audience and another one from the present that we will send you.
Thank you very much. And again, I do appreciate the flexibility, and I hope to get the chance to meet everybody soon.
Thank you. Thank you.
Thank you.